To everyone joining me this morning, good morning. Mr. Ishover here. We continue with our derivative topic. We have up till now talked about derivatives of polynomials, followed by the chain rule and then the product and the quotient rule. The chain and the product and the quotient rules are very important because they will show up in any kind of trigonometric function, derivatives, or any functions thereafter in the following videos. Those three rules will show up too frequently that you don't want to ignore them. Now, trigonometric function derivatives are not difficult by any means, but unlike the polynomial derivatives where we had the formula, a template which we could easily follow and which yielded us the following technique for determining the polynomial derivative, there is no such template or scheme which applies for the trigonometric derivatives, the functional derivatives of the 6 trigonometric functions. There is no such template that you can use. So basically you're left with two options. One that you just memorize them, and the other you choose not to memorize them and you keep referring back to your reference page. So you basically won't have a specific scheme to follow. You either know the derivatives of these 6 functions or you just keep referring back to your sheet from your textbook, and there's nothing wrong with either option. But you can derive these, and we don't have to get too much into the derivation process because we're just doing survey video over here of trigonometric functions. But you will see in the questions that I present, you will see the product, the chain rule, and the quotient rule apply. So when it comes to these 6 trigonometric functions, if you are given the following 2 derivatives, wherever you see the sine x and you were to take the derivative of it, you would get cosine x, and wherever you saw the cosine x function and its derivative was provided and you knew it to be minus sine x, you can derive all of these from just knowing those two. And that's what we're going to do over here, followed by some examples. Now look over here. The tan x is a composite function in the sense that it is made, well, I should have said it's a compound function. It's a compound function made up of 2 functions. Now look over here. If you have to find the derivative of tan x, the derivative of this function tan x, and you are given these two, look what you do over here. After this step that I'm showing you, you know this tan x can be represented in this format. You don't have to do any plugins yet, but look what happens. If you look over here, it looks like a rational function for which you would apply the quotient rule. If you went ahead and you did the quotient rule over here, you take the g function, which is cosine x, and you'd multiply that by the derivative of your f function, which is sine x, and you'd minus from that the original f function, and multiply to that the derivative of the g function cosine x, and you do the square of the g function. You know, this is a template here for the quotient rule. Now look over here. If you carry all of this out using what I've told you over here, the cosine x multiplied by the derivative of sine x, which happens to be a cosine x, minus this original sine function, which is your f of x. Remember, this right here is my f function, this right here is my g function, and the derivative of cosine x, which happens to be a minus sine x, and it's all over cosine square x because it's always over g squared in that quotient formula. But look over here, let's start bringing things together. You have a cosine square x, and you have a minus multiplying with this minus, giving you a sine square x, and then you have a cosine square x here in the denominator. And this is why you have to know trigonometric identities as a precursor to getting into calculus, because here's a trigonometric identity, one of your Pythagorean identities. Cosine square x plus sine square x equals 1. You get a 1 over cosine square x, and that in itself represents secant square x. So now you know that the derivative of tan x is equal to secant square x, and we can just plug that over here. I'm just basically writing here a cheat sheet over here of the various trigonometric function derivatives you should know or you should memorize. Given these two from the beginning, you can determine those. So we've done the tan x. Now let's look at some more. Let's look at the remainder. If you are now tasked with finding the derivative of cotan x, the derivative of cotan x, and in all of these x's you can put thetas, and you could actually let's actually do that. In all of these places of x, you're by no means required to bind yourself to the variable x. You could have done theta and then you just replace the d over d theta with the dx with the d theta. There's nothing wrong with doing that. If you know cotan to be a compound function of cosine theta over sine theta, you can again apply the quotient rule and determine the derivative of cotan function. So let's look at the quotient rule. You know the quotient rule from the previous video. You'll multiply the original g function and multiply that with the derivative of the f function. Here's my f function, here's my g function, and you'll minus that from the original f function and multiply that with the g function derivative, which is sine theta, and this is going to be all over the square of the g function, the square of the g function. Now you gotta just do the parts on the top. There's no chain rule kicking in here because these are not composite functions. Sine theta is multiplying by the derivative of cosine theta, which is minus sine theta, x's and thetas are all the same, minus cosine theta multiplying by the derivative of sine theta, which is cosine theta, all over sine squared theta. Now what do we get over here? Minus sine theta times sine theta is a minus sine squared theta minus cosine squared theta all over sine squared theta. All of that is beginning to make sense. Here in this top numerator area, if you isolated a minus 1, if you isolate a minus 1, you can do sine squared theta times cosine, well we have a plus over there which will kick in, a plus will kick in over here, plus cosine squared theta all over sine squared theta. Now look over here, this right here is a Pythagorean identity. This will become a 1. This right here will become a 1 times a minus 1. You get a minus 1 in the numerator. So all of this boils down to, if you look at all of this, it will all boil down to a minus 1 in the numerator, and in the denominator you'll have a sine squared theta. When you simplify it out, you'll get a minus 1 divided by sine squared theta. If you flip everything around, what do you get? You get a minus cosecant squared theta. You see, you get a minus cosecant squared theta. This right here, this whole part right here is equivalent to this over here. So now when you look at this run through of this process, you know that the cotangent x is equal to minus cosecant square x. The derivative of cotangent x function is always minus cosecant square x. These could have been thetas here, would have been fine. But you see how the cotangent derivative has been derived for you. We're going to do the next two, and then we'll be looking at examples. Let's continue the derivation process now with these two remaining. Remember, I started this entire process here by providing you these two. Once you have these two, you can determine those. Once you know all of these, commit them to memory or put them on your reference sheet and keep referring to that sheet as you look through your questions. The derivative of cosecant x is not difficult at all. If you view it in this form, 1 over sine x, you have two options of proceeding over here. You can use the quotient rule, given that this right here represents your f function and this represents here your g function, or you can rewrite this out in another format and use a chain rule. Like if you brought the sine x, you could say it's to the power of minus 1. You could view it as d over dx sine x now to the power of minus 1. Now you have a composite function, a single f function but a composite function, and you can use a chain rule and you can proceed in either direction and obtain the right answer. What I will do is I will use this function over here for the cosecant derivation. I'll use a quotient rule, but when I go to the secant rule, I'll convert it in the other way and we'll use the chain rule that way. So using the quotient rule over here, we know we have the g function multiplying by the derivative of the f function, which is 1, and the original f function now multiplying by the derivative of the g function, which is sine x. You know this right here is all basically the template for the quotient rule. G times the derivative of f minus f times the derivative of g divided by g squared. You know the derivative of a constant is always 0. This 0 will zero out everything over here. So you're basically left with everything from this minus sign onward. So you have a minus on the top, minus 1. The derivative of sine x is a cosine x. You get a cosine x. And on the bottom, you basically just have a sine square x. What you do here is open this up by this means. Look, cosine x divided by sine x times 1 over sine x. You still have the same thing here. These two are still equivalent, but you are opening it up so you can get your final answer. Your final answer is going to be a minus cosine x divided by sine x is a cotangent x, and a 1 over sine x is a cosecant x. Look over here. The derivative of a cosecant x is always equal to minus Cotan X, cosecant X. That's your answer right there. Not a single function, but you have a double function over here coming together in a times relationship, a product relationship. We will look next finally at the derivation of the secant X derivatives, then we'll look at some examples, worked out examples. When we're looking at the derivative of secant X, and I said I'm going to use a chain rule over here now, we know it's the same thing as looking at it in this form, 1 over cosine X, because secant X is the reciprocal of cosine X, and you can also look at it in this form, cosine X to the power of minus 1, a composite function. So let's look at it using the chain rule. If u is equal to cosine X, then f of u is equal to u to the power of minus 1, right? U to the power of minus 1. So let's bring in the chain rule. Derivative with respect to u, u to the power of minus 1, and the derivative with respect to your x, your variable, cosine x. Now all you gotta do is individually solve these out and take it to completion and you'll be done. The derivative of u to the power of minus 1 is just basically the polynomial scheme. Minus 1 will come over here and the exponent will be reduced by 1. You'll get a minus u to the power of minus 2, and of course you have to substitute back in here at the end. The derivative of cosine x is a minus sine x. This minus and this minus can cancel out, so you can just eliminate these. These minuses will cancel out. Now look over here, u to the power of minus 2 is 1 over u squared, because the minus indicates a reciprocal effect, and the sine x is on the top. You end up with having this. When you resubstitute back in place of u, and u, you know, represented cosine x, you end up with cosine square x. But you can open this up again like you did previously, sine x over cosine x times 1 over cosine x, which you know to be tan x secant x. I'm just rewriting these in a single functional format. This is tan, this right here secant. So the derivative of secant x is basically tan x secant x. That's what it is. Tan x secant x. But now you have all the 6 derivatives laid out for each of the 6 trigonometric functions. And we're not talking about inverse trigonometric functions, we're talking about the regular trigonometric functions. Now these will be the derivatives which we will use in our questions as I present them. Here is our question. We have to find the derivative with respect to theta. Theta or x could be the same over here. And our function is this, 4 sine 3 theta. If I were you, I wouldn't look at this as a separate function here and look at this as a separate function and think of the product rule. What I would do is I would bring the 4 out and look at it as just a single function. You see the 4 can come outside everything, and then you work only with the item in between using now, instead of the product rule, you use only the chain rule. Otherwise, if you're doing it this way, you'd be using the product rule and the chain rule at the same time. But here you've simplified it simply by bringing the item out, removing it from the derivative. Nothing wrong with that. Now you have to use a chain rule, and you can say substitute u is equal to 3 theta, because this right here is a composite function. 3 theta represents a composite effect over here. If u is equal to 3 theta, f of u is equal to sine u. And now you develop your chain. Look, 4 times derivative with respect to u, sine u, and the derivative with respect to the theta, which is 3 theta, and you'll do the individual derivatives over here and you'll carry it through. The derivative of sine u is going to be cosine u. Cosine u, and you have to still substitute back into u at the end. The derivative of 3 theta is going to be just 3. Why? Because 3 theta over here represents a theta with a power of 1. 1 multiplies with the 3, it gives you the 3, but the 1 exponent is reduced by 1. You essentially get 3 theta to the power of 0, which is just a 3. Remember, this is just like a 3x. You're doing the same polynomial derivative scheme over here. When you multiply all of these coefficients, 4 and 3, you get a 12 cosine u, but you got to resubstitute back in u for this part right here. The u was equal to 3 theta, so your final answer is 12 cosine 3 theta. And that right here represents your final answer. The derivative of 4 sine 3 theta is 12 cosine 3 theta. And you have a good answer over here, and it's right. Now in this question you have to find the derivative of this function over here. Now it would look very much close to this, but it's just a coincidence. Our function is actually this. And you know you have 2 functions. Here's your f function, here's your g function. They're multiplying, so you have to use a product rule. And I'll just abbreviate that as a PR, the product rule. And you know there's a template for that which I brought up in the previous video, and we will proceed exactly as that. So the derivative would be the g function multiplying with the derivative of the f function, which is secant theta. Then you add to that the original f function, now multiplying by the derivative of your g function, which is tan theta. Remember, I'm laying it out, I'm not doing the actual derivative step. That's in the next part now. Now tan theta will multiply with the derivative of secant theta, which you know right here, tan theta secant theta. I'm just changing the x's here for theta because I'm doing everything with respect to theta over here. Plus secant theta multiplying now with the derivative of tan theta, which is secant square x, but here will be secant square theta. Combine the terms. Tan theta will multiply with this to give you tan squared theta secant theta, plus here you'll get a secant cube theta, because this is secant to the power of 1. 1 times that 2, 1 plus that 2 will give you that 3, because you have same bases, the exponents will add. Now you can bring this to completion by finding a like term. I have a like term over here of secant theta because it's present in both, and it'll go in here, tan squared theta plus secant square theta, and I believe we will be done with this right here, and that'll be our final answer. Let's look at more examples. Now look over here at this function here, 1 minus sine x divided by the cosine square x. You know, we're clearly looking at a rational function over here. We'll be using the quotient rule. That's obvious. We have two functions dividing. Here's my f function, here's my g function. They're both dividing, so we'll use a quotient rule, QR for quotient rule. And look over here, this right here represents a composite function. It's not simply cosine x, but it's cosine square x. So we know we'll be using the chain rule. PR, QR, CR, product rule, quotient rule, and chain rule. Alright, so we'll be using both of these rules. The chain rule will kick in at the appropriate step. So you have to use here the template for the quotient rule, and you know that to be the g function, original g function multiplied by the derivative of the f function, which we have to still calculate, minus the original f function multiplying by the derivative of the g function. But here we have to bring in the chain rule, all divided by the g function squared. Now let's carry this further. Let's create some space over here. Let's work it out as we go through. The derivative of 1 minus sine x involves a derivative of a constant and a trigonometric function. The constant will zero out, so you basically have cosine square x multiplying by the derivative of minus sine x. If the derivative of sine x is cosine x, the derivative of minus sine x will be minus cosine x. Because the derivative of sine x, you know there's a cosine x, but there's a minus attached with it, so the minus sticks with it. Now look over here, let's bring in the chain rule. You have the original f function over here multiplying by the cosine square x. If u is equal to cosine x, then the substitution will lead you to this. If u is equal to cosine x, f of u is equal to u square. The derivative with respect to u is u squared times the derivative with respect to x, cosine x. Now this of course is all divided by your cosine. Let's make this to the power of 4x because I've opened it up. Cosine square x square is a cosine 4x. Now we have to just basically finish this up. On the top I have a cosine square x times a minus cosine x. I get a minus cosine cube x. Here, well, I want to try to do this in one step over here. Let's come over here, work here on the side. This u derivative of u squared will become a 2u, and the derivative of cosine x will become a minus sine x, because you know here the derivative of cosine x is a minus sine x. So this right here yields you that. But then you gotta look at it as minus 2 sine x and u. But what is u? It's minus 2 sine x, and u here represented cosine x. This right over here represents everything right from here up to here, which has to multiply by this over here. It has to multiply by that. So let's do that multiplying and bring it over here. Minus 1 minus sine x times all of that will give you, let's bring in a parentheses, 1 will multiply with that and it'll give you minus 2 sine x cosine x, and then the minus sine x will multiply with that and give you plus 2 sine square x cosine x. Okay, and you're going to have this all over your denominator, cosine to the power of 4x. Now we just have to simplify this part here in the numerator, and then we are done with this question. So let's open this up over here. We'll just finish this up in this last step. We don't have to get too fancy. But when you open this up right here, you get minus cosine cube x. This minus and this minus will give you plus 2 sine x cosine x. This minus with this minus 2 will give you a minus 2 sine square x cosine x all over cosine to the power of 4x. This right here will represent your final answer. I want to write it here again just for neatness sake. You'll have a minus cosine cube x plus 2 sine x cosine x. Then you'll have a minus 2 sine square x cosine x all divided by cosine to the power of 4x. It was a little bit of a tricky question, but it wasn't hard. It was more cumbersome than anything. But here is your final answer, and it's done. The derivative of this entire function is right over here. You could have simplified it because you can see cosine x, cosine x, cosine x is in all of these. When you isolate that cosine x, you could have reduced the power of the denominator because you would have brought out a single cosine x. And then this denominator would cancel out with that, and you get a cosine cube x in the denominator. But you can do that on the side on your own. I was just showing you the general scheme of this question. Our function is this, and we have to find the derivative of this function, and you know it's made of the product of two individual functions, but there's nothing composite about them. Here's my f, here's my g. These are single functions. There's no composite in this true sense, so you're not going to be using the chain rule. You'll only be using the product rule over here, and that makes this question easy. You're going to look at the g function and you multiply it by the derivative with respect to theta of your f function. You'll add to that the original f function now multiplying by the derivative of your g function, which is secant theta. In this next step, we'll actually bring in the derivatives. The derivative of cosecant theta, as you know, is minus cotan x or cosecant x, but you can use the theta variable over here, minus cosecant theta, cotan theta, plus cosecant theta. The derivative of secant theta is secant theta, tan theta. Remember, if you do this enough, all of this comes automatically into your memory banks, and then you're good. You gotta just open it up. Secant theta times minus cosecant theta, you can just write it all out. Let's not forget the minus sign. Minus secant theta, cosecant theta, cotangent theta. We'll have to simplify this out because there's something that might cancel out. Plus cosecant theta, secant theta, and tan theta, and of course something will simplify out over here. What I mean by simplifying will become evident here. You'll have a minus 1 over cosine theta because that's a secant theta, 1 over sine theta, which is a cosecant theta, and then you have a cosine theta over a sine theta, which represents your cotangent theta. You see, you can multiply, you can cancel something out. Cosecant theta is 1 over sine theta, secant theta is 1 over cosine theta, and each of these individually are in a product relationship. And then you have a sine theta over a cosine theta. Now look, over here in this first part before the positive sign, let's make this better. Before the positive sign over here, you can cancel out this cosine and you can cancel out that cosine. You get left with a 1 over sine theta times 1 over sine theta, which is a 1 over sine squared theta. When you bring it up, you get a cosecant squared theta. And let's not forget the minus sign right over here. You see that 1 over sine theta times 1 over sine theta is a 1 over sine squared theta. You bring it back up, it's a minus cosecant squared theta because here's my minus sign right here. Now let's look over here. This sign multiplies by with this, and you get a 1 over cosine theta times a 1 over cosine theta, which is a 1 over cosine squared theta, which if you flip it up is a secant squared theta, and this would represent an answer that you can be good with, that you can be happy with. This question over here will prove to be fun because you know you have a chain rule which is coming in, and you can eliminate the need for a product rule by taking this coefficient and pushing it outside. So you can look at the whole question as 7 derivative in terms of, let's use only one variable. I've put a theta over here and an x, which is wrong. If I'm using x, I must use x. So derivative with respect to x multiplying as a coefficient now because I moved it out, and now I have my tan 5x inside. I have to use a chain rule over here because this right here is a composite function. If u is equal to 5x, then f of u, your function has now become tan u. Tan u. So this is where the chain rule will kick in. 7 times derivative with respect to u, tan u, and then the derivative with respect to the x, 5x. You just have to find the derivative over here, and you have to find the derivative over here and multiply everything across. You still have the original 7, and the derivative of tan u, you know, is a secant square u. Secant square u, you'll have to resubstitute back over here, and the derivative of 5x is just simply a 5, because now you know this is a 5x to the power of 1. That 1 multiplies with the coefficient, and the 1 exponent is reduced by 1 to give you x to the power of 0, retaining you just the coefficient, the 5. When you simplify this, the 5 multiplies with the 7, you get a 35 secant square u, and you resubstitute your u value, which is right over here, your u value, 35 secant square 5x, and you're done. So this right here represents your single derivative. Now why am I talking about single derivative? The single derivative symbol is this because there will be questions, and we'll see down the road, where you will do a double derivatives. You'll do a derivative on top of a derivative, but that's a subject matter of another video. Now you would take this value and run the derivative through this, and you get the second derivative. When you do a derivative on this, you get the second derivative. Second order derivative. But right now we're only talking about first order derivatives, or the first step derivatives, which are symbolized as y with a single prime. Double derivatives would be y with a double prime, which is the same thing as doing a derivative and then a derivative on top of that with your answer. A subject matter for another video. We'll look at a few more examples and we'll be done with this subject. Let's focus here at this question. We have to find the derivative of this function, which you know is a rational function. It's made up of an f component and a g component. You know we will be doing for sure the quotient rule over here, but you also know here in the numerator we have a composite function, so we'll be using a chain rule as well, composite function along with the quotient rule. So we have to begin with the template of the quotient rule. We'll multiply, as we do the derivative question, we'll multiply the original g function with the derivative of the f function, which is going to be cosine x squared, but we'll have to bring in the chain rule over here, minus the original f function over here multiplied by the derivative of the g function divided by the g function squared. Root x times root x will just give you an x, so we're good with that. Let's bring in the chain rule over here. Let u equals x squared. If u is equal to x squared, then f of u is equal to cosine u. So let's bring that in. Root x times derivative of u will be cosine u, and then du to dx will be your x squared minus cosine x squared times the derivative of root x all over x. Now in this next step we're actually going to do the solving. I was just laying it out over here with regards to the chain rule. Over here our chain rule is laid out properly. Root x will multiply over here with, what's the derivative of cosine u? It'll be minus sine u. Minus sine u. What's the derivative of x squared? It'll be 2x, as you know, easy. Polynomial scheme you'll use over there. Minus cosine x squared. What's the derivative of root x? By now you know it'll be 1 over 2 root x, because when you carry it through the scheme, you'll always end up with a format of that. All over x. All over x. Let's come over here and let's do some working out over here. This 2x multiplies with this root x and with that minus to give you a minus 2x, x to the power of 1 times x to the power of 1 over 2, x to the power of 3 over 2. We're not going to take this out to the extreme levels of simplification, but we'll take it out to a reasonable level. Sine of u. Let's replug in the u. What was u over here? It was x squared. Sine x squared. Minus cosine x squared over 2 root x. Cosine x squared divided by 2 root x all over x. You could be fancy and you can do a common denominator over here and then get rid of this common denominator by taking everything down. You could do all of that, but I won't. In the interest of space, I won't do that because that's the algebra part, and which is not hard. You can do that on your own. So, but you're going to have to take the common denominator over here, rationalize, and bring everything into a single denominator, and then that'll be your final answer. But we can stop over here because I'm showing you how the scheme worked out. The derivative part is done. Now it's just the algebra simplifying part. and then that'll take you to your eventual final answer. But this question over here, for the purposes of this video, is done. Let's look at a few more examples. Here is an easy question. You know you have two functions over here. This is your one function, this is your other function. Here's my f function, here's my g function. G is the composite function. The two functions are multiplying, so we're looking at the product rule, and we'll also be looking at the chain rule over here. And the chain rule will kick in at the appropriate step. But let's start with the template for the product rule. It will be the g function, which is sine 2x multiplying by the derivative of the f function, which we will find, plus the original f function multiplied by the derivative of the g function. Now let's bring in our chain rule earlier than normal. If u is equal to 2x, then f of u is equal to sine u. So derivative with respect to u, you're going to put a sine u over here, and then the derivative with respect to the x of this u function will be the 2x over here. Now we open it up with the derivative. Sine 2x, which is your original g function, will multiply by the derivative of x, which is just a 1. Plus x will multiply with the derivative of sine u, which will be cosine u, as you see right over here. Derivative of sine is a cosine, and the derivative of 2x will be just a 2. Now marry things up. Sine 2x times 1 is just a sine 2x. 2 can multiply with this x to give you that coefficient 2x, and then cosine u, resubstitute back over here, 2x, and you're done. You're not going to start isolating 2x's over here, because 2x over here represents your angle which the functions are applying with. So you're not going to isolate a 2x and then do that. There's no isolation over here. This right here represents your final answer. This question is done. This should be an easy question over here. You have to find the derivative of this function, 1 plus tan theta in the square root. You know there's just a single function over here, it's just an f. I'm not seeing a product rule or chain rule coming into play, but I'm seeing a composite function, so I know I will be dealing with the chain rule over here. If I want to start with the simple substitution, I can say u is equal to 1 plus tan theta. Therefore the function with respect to u must now be root u. So the chain rule will come off from these substitutions you made. The derivative with respect to u will be just root u, because that's your function with respect to u, times the derivative with respect to theta, because our variable here is a theta, will be just your actual substituted item, 1 plus tan theta, or expression. Now you actually have to do the derivatives, and you know by now anything which looks like this is always 1 divided by 2 times the root of whatever variable you're looking at. Here the variable is u, so we'll put u, multiplied by 1 plus tan theta derivative. This is like a polynomial now, except it involves a trigonometric function. The derivative of a constant is always a 0, so the 1 is meaningless here. But the derivative of tan theta is exactly what you see over here, secant squared theta. Bring things together, you'll have a secant squared theta in the numerator divided by 2 root u. But what was u? It was 1 plus tan theta. 1 plus tan theta. So that represents the final answer. Let me write it over here in a more neat manner. Secant squared theta divided by 2 times 1 plus tan theta. If you want to be high speed, you can multiply the radical. You can rationalize the radical. Take this root 1 plus tan theta over here and multiply in the numerator and the denominator like you would do this. Only the radical part. You don't have to rationalize it too. And you do it over here in the denominator, 1 plus tan theta, and if you did that you would get another finalized answer without a radical in the denominator, and your answer would be this, and it would be just fine. Secant squared theta times 1 plus tan theta, nothing wrong with doing this as an answer, divided by 2 times 1 plus tan theta. And you could even open this up, you can say 2 plus 2 tan theta, but this right over here would be a good answer. And if you want, what I presented here originally without rationalizing was also a good answer. So this question was not hard by any means, but it just depended on how far you took it. And our derivative question is this. We have to find the derivative of this function, cosine of this value. It's not going to involve the product rule or the quotient rule, but it will involve the chain rule, because this is not a cosine theta. Theta here represents an expression, or x, I mean cosine x, but this is a composite function, so we have to use a chain rule here for sure. And you have to make a substitution. If u is equal to x squared minus 2x plus 1, then f of u must be equal to cosine of this u value. So here in this type of question, you're seeing the derivative of a trigonometric function involved with the derivative of a polynomial, which is fine. You'll have a mix of questions involved. You could have multiple functions in the same question, and you have to use the different schemes or the templates for those various derivatives. So let's bring everything together. You have derivative with respect to u is cosine u, and the derivative with respect to x will be x squared minus 2x plus 1. You have a polynomial derivative playing here, and you have a trigonometric derivative playing over here. The derivative of cosine u will be minus sine u, because you know that from right over here. And the derivative of this polynomial, using that scheme, as you know, a x to the b, you know b becomes attached with a, you have x to the power b minus 1. You see the scheme over here? We know the scheme from the very first video. This is the scheme you have to follow over here. You get 2x minus 2, simple as that. If I were you, I would look at this minus over here, and I would look at this and treat them as coefficients, and I would bring them together. I would get minus times 2x is a minus 2x, and minus times 2 is a 2. I would get a 2 minus 2x as my coefficient. If you look at this, minus 1 times 2x minus 2, the coefficients, I'm treating this as a coefficient, the sign, and this as a coefficient. When you open this up, you get a 2 minus 2x, which is what I've done, because I'm trying to make things look clean. 2 minus 2x times sine u. What's my u over here? This entire x value, the angle value, x squared minus 2x plus 1. And this right here is a good answer, and you're done. Easy, but you're done. And if you had a value, if you had an x comma y value, you take the x values and plug them right over here. You'd plug them right over here, and you plug them right over here. You'd calculate all of this out, and it would give you your instantaneous rate of change for the tangent line, the slope of that tangent line, and you could also determine your equation of the tangent line using the slope value and this coordinate value. We'll be looking at some interesting questions over here, and you can see for the space reasons, I've eliminated the write-up over there on that side of the board. As needed, I'll be talking about the various derivatives as they come along. When we're looking at this function, y is equal to, or f of x is equal to this, and we have to find its derivative, it's not a very difficult process. You have to recognize over here that we might be dealing with two composite functions, and we may not be seeing the product or the quotient rule play over here, which is fine. It's like a polynomial of two composite functions. So if we make some substitutions, let u is equal to secant x, then f of u is equal to u squared, and another one can be v is equal to tan of x, and then f of v is equal to v squared. We can plug these in using the chain rule. It's not too hard. Yeah, and your chain rule would proceed in this manner. As you will see, I laid out over here. Derivative with respect to u, using our u substitutions for this first part over here, and the next part will be right over here. Let's get this started. Derivative with respect to u, we'll put a u square over here, and then the derivative of that u with respect to its variable, secant x, and then here's our plus sign. Let's do the v aspect for this second part. Derivative with respect to v will have a v square, and then the derivative of that v with respect to its variable, you'll have a tan x. So now you know you got two trigonometric function derivatives that you need to know. Not too hard. Well, we'll proceed from this left side and we'll go towards the right. The derivative of u squared will be a 2u. The derivative of secant x, as we know, will be secant x tan x. The derivative of v squared will be a 2v, and the derivative of tan x, as we know, is a secant square x. Now what remains is to actually plug in the u and the v values. You know the u value over here happens to be a secant x, and then it's still multiplying with the secant x tan x, and then the v value over here happens to be tan x, and it's multiplying with secant square x. So all you gotta do is do this complete multiplication here, complete multiplication, and see what you end up with. You end up here with a 2 secant square x tan x, and here you end up with a 2 secant square x tan x. You're essentially ending with, on both sides of this positive sign, they're both identical terms, 2 secant square x tan x and 2 secant square tan x tan x, and they're just basically doubling up. So your final answer is going to be, here's the equal sign, it's going to be 4 secant square x tan x, 4 secant square x tan x, because these were two individual terms which are adding up. So the 2 and the 2 coefficients add up to a 4. So you get a good answer here, 4 secant square x tan x. Not a bad question at all. Now this question over here, y or f of x equals sine of this value, over here, it will prove to be an interesting question because it is a composite function, but within the composite function you have a product of two individual functions. But it shouldn't be too hard. I would proceed with this using the chain rule, because if I'm looking at all of this as a single function, I have within this composite aspect right over here. So I should just proceed ahead with the chain rule. If the product rule formulates after the application of the chain rule, so be it, then we'll proceed with it from there. But I wouldn't like separate these into separate two functions like an f and a g and then proceed with the product rule, because the part in the parentheses represents the angle or the theta value of the sine, so it's really like part of the same function. We have to do a substitution over here. If u is equal to x cosine x, then f of u must be equal to sine u, and we have to proceed with the chain rule here initially. So we do a derivative. Because we're finding the derivative of this function over here, we proceed with the chain rule. The derivative with respect to u will have a sine u over here, and the derivative of that u with respect to its variable is an x cosine x. Now look over here. Now you have essentially separated the composite function into its separate parts. Here now you might want to think about applying a product rule separately, and that's what we'll have to do. If this now x here represents an f function and this cosine x represents a g function, now you can think about applying the product rule, and all of this will still multiply with the result you'll get over here. It'll prove to be a very interesting question. So let's look over here. Derivative du and then sine u, because I'm not solving these out yet. Now let's look over here. Derivative of u with respect to x, let's make a little square brackets, because here we're going to do our product rule. If this is my f and there's my g, we're going to have to run it that way. Cosine x, now we're applying the product rule template. Cosine x times the derivative of that x, the f function, plus the f function times the derivative of the g function, cosine x. You see how all of this is playing out? But this still is multiplying with all of that. Now look over here. The derivative of u with respect to u of sine u, and then du over dx. Look over here. Cosine x will multiply with the derivative of x, which is just 1, and you'll get a cosine x over here. Now x will multiply here with the derivative of cosine x, and you know the derivative of cosine is a minus sine x. Now look what we're getting over here. Let's open this up. Sine u will become cosine u, and then du to dx. And now look over here, we have cosine x minus x sine x. Cosine x minus x sine x. So now you see how we're playing this through. Now technically this step of du or dx has been completed, because the du or dx step, this step over here, right here, now you don't have to start doing a new derivative of all of this, because the du over dx step right here and right over here in this area right over here, you see where this arrow is, became replaced by the product rule, because we instituted the product rule over here. So now you shouldn't be opening this up and now doing a new derivation of it, because you've kind of already done the derivative over here. All you have to do is substitute u and open everything up. Look what happens when you substitute u. You get cosine, and your u value was this x cosine x, x cosine x multiplying by cosine x minus x sine x. And that I believe to be a very good answer. It should be a right answer right here. This right here is our final answer. You could have written this part first and then this part second, or you can write this part first or this part second, but they're both in a times relationship. They're both multiplying with each other. So an essential thing over here to note is we started with the chain rule, but we brought in the product rule afterwards. You still kept everything going, but here don't make the mistake of redoing a new set of derivatives over here, where this cosine x would become a minus sine x, and then you start reapplying a product rule. You don't want to do that, because from this step onward, this chain rule got overtaken by the product rule, and then that product rule carried you down to your final answer. A very interesting question. Let's take a look at this question. Y, or f of x, is equal to cotangent square of sine theta. Now you know you're looking over here at a composite function, but you might have more than one king, because you have a sine theta representing a composite function, then on top of that you have a square. So you might have double chain rule applying over here, but I'm not seeing the application here of a product rule or the quotient rule. So we have to proceed here with an initial substitution. My initial substitution will be to look at all of this as one item. Look over here, look what I'm doing. If u is equal to cotan of sine theta, then f of u must be equal to the square of all of that, u square. See, all of this u square. And now we'll have a second substitution kick in, but at the appropriate step. Let's proceed with using that substitution. So the derivative with respect to u, and it's a u square, and then that derivative of u with respect to its, well, I should not be putting an x over here because we have theta. With respect to its theta value, now you have cotan of sine theta. Now don't confuse this as being a product rule applying over here. This is just its trigonometric function with its angle over here. So you still have a chain rule application, not a product rule, but you have a composite function still over here. We have to bring in a second substitution. If v is equal to sine theta, then f with regards to that v must be cotan of v. So we have to bring in a second kink over here. So the derivative with respect to u and u square, and the derivative of that u with respect to this new kink that we're adding over here, the v value, with respect to the new v substitution, must be cotan of v, and then the derivative of v with respect to its theta must be sine theta coming over here. So now we have done the complete application of the chain rule with double substitutions kicking in. All we have to do is now the individual derivatives of everything. U square as a derivative will become 2u. Cotan v, you know cotan is a minus cosecant square v. You remember what I had over here on the side, which I've erased. Sine theta derivative is cosine theta. Do these enough and you'll memorize everything. Now bring all the coefficients together. You have a 2 and a minus. I'll bring the minus and the 2 together. I have a u over here. I want to substitute back the u. The u was cotan of sine theta. And then we have a cosecant square. And the v was what? Sine theta. We can bring this all in parentheses, and then we have at the end cosine theta. A better way to write all of this is to write the individual functions first and the compound functions second. So this is how you could rewrite everything as minus 2 cosine theta, because a cosine is like a singular function. It's not a composite function. Then write your composite functions. Then you can write cotan of sine theta, and then you can write cosecant square sine theta, and you would be good to have done that. It would be a good answer, a right answer. This right here would represent your final answer. The derivative of this composite function will be right over here. A complicated answer, but a sensible answer. Here is an interesting question. F of x or y is equal to root x times cosine of root x. If you look at it carefully, this right here represents your f function, f of x, and this represents a g function. You have a product rule applying over here, and the g function happens to be a composite function. So you have to proceed knowing that you have to apply the product rule and you have to apply the chain rule actually, because it's a composite function. So you have to proceed in that way. So you have to bring in the template for the product rule, and we know what that is. You take the cosine root x, which represents your g function, you multiply that by the derivative of your f function, add to that the non-derivative, the unedited f function, multiplied by the derivative of your g function, where in the next step you'll be applying the chain rule over here. You know, if u is equal to root x, then f of u is equal to cosine u. For this chain rule substitution, that's stuff you're going to bring in. So let's look at this next step. Cosine root x, derivative of 1 of root x, you know it's going to be 1 over 2 root x, and we know how to do that now. It's all too frequent of a sight to do a derivative of a radical. Plus root x, let's bring in the chain rule or derivative with respect to u. You're going to do cosine u, and then the derivative of that function u with respect to its variable is going to be root x over here. In the next step, let's start completing things up. You have root x over 2 root x. I'm just writing this in the denominator format over here. Plus root x times cosine u is a minus sine u, and derivative of root x will be 1 over 2 root x. So let's write that 2 root x, 1 over 2 root x. So now you have common denominator over here. But you see this minus sign is going to affect you over here and make it a minus. So let's write it out. Cosine root x minus root x sine u, and u over here was a root x. We have resubstituted back for that value of that u, and we have a root x over here. So now you're saying that our equation over here has come to its completion, because If you want, you could rationalize as root x, multiply root x here and root x over here, but you don't really have to. This answer right over here is good. If you did rationalize it and you took root x over here and root x over here, your next answer, or your answer would be root x cosine of root x, because root x is now serving as a coefficient, and this root x would multiply with this root x, you'll get an x over here. Sine root x here in the denominator, you'll get a 2x, because root x times root x is equal to 2x. So this can serve as one answer, and this can serve as another answer in a non-rationalized manner, but they're both good answers, and it was a very good question. I enjoyed this question. Let's look at this question. I promise you this question will appear to be a very interesting question. We're looking at a rational function, and you're going to be using for sure the quotient rule, but we're also looking at these composite functions, because secant 2x and 1 plus tan 2x are composite because they have a 2x and a 2x. If this represents in the numerator your f function and the denominator your g function, we have to start by using the template for the quotient rule, and you're going to do exactly that. You're going to start with the template of the quotient rule and start doing 1 plus tan 2x, which is your g function, multiplying by the derivative of the f function. Now look at the f function, it's a composite function. If you make a substitution u is equal to 2x, then f of u must be equal to secant u. So let's bring that in. Derivative with respect to u, you have a secant u, and then the du with respect to its x value, you have a 2x. Then you know the quotient rule has a minus, we have to bring in that minus. And now let's look at the f function right here, secant 2x, which is going to multiply by now the derivative of this denominator, the g function, and you have to do another substitution over here. If v is equal to 2x, then f of v is equal to 1 plus tan v. That's going to be our substitution over here for the v. So derivative with respect to dv, you're going to have a 1 plus tan v. And now I have to make a little bit of space over here. We know our v substitution is 2x. There's nothing wrong with erasing that away. We know what it is. And then derivative with respect to its x value is 2x. And you know all of this is going to be dividing by this g function, but to the square, because it's always over g squared. Now let's try to do expediting some steps over here. We have 1 plus tan 2x. Derivative of secant u is going to be secant u tan u, because the derivative of secant function is always secant x tan x. Derivative of 2x is just a 2, and how about I just bring the 2 here as a coefficient here at the very beginning, my 2 over here. Now let's look at this minus sign, and over here at this part I have a 2x, the derivative of that is going to come out as a 2. I have a secant 2x which stays unchanged because that's your f function unedited. Then I have a 1 plus tan u. When you do the derivative of this polynomial over here with a trigonometric function, the 1 zeroes out, but the tan u, the tan v becomes secant square v. And you know all of this over here is divided by this denominator 1 plus tan 2x squared. And sometimes these questions can get a little messy. Now what we have to do is our substitutions over here. Substitute for u and substitute for v. I have a 2 times 1 plus tan 2x secant 2x tan 2x, because u here was a substitution for 2x, and 2 secant 2x, and then secant square v was again a 2x, we know it was a 2x, and this was over 1 plus tan 2x squared. Now to finish this question we have to recognize some commonalities. I am seeing common terms. In the numerator I have a 2 over here and I have a 2 over here. And in the numerator I have a secant 2x here and a secant 2x over here. And you can isolate 2 secant 2x. Watch. I'll isolate a 2 secant 2x and it'll go into this first part from here to up to the minus sign. It'll go 1 plus tan 2x times, and then you have a tan 2x still over here. Then you have your minus sign. Now this secant 2x goes in all of here. Secant square 2x times secant square 2x. This right here is divided by our denominator 1 plus tan. Let's be neat over here. 1 plus tan 2x square. Now the fun part. The fun part is this. If you open up this parentheses over here, what will you get? Let's put it over here. You'll get tan 2x and this tan 2x will multiply with this tan 2x, you'll get plus tan square 2x. That's what you'll get if you open up just this parentheses part. You'll get tan 2x plus tan square 2x, and after that you have a minus secant square 2x. Now look over here. I'm just for the space reasons, I'm doing this part right over here. Now look over here. If you have tan 2x plus tan square 2x minus secant square 2x, this right here represents a trigonometric identity. If you think back to trigonometric identities, tan square plus 1 is equal to secant square x, right? But if you shuffle this around, tan square x minus secant square x is equal to minus 1. So all of this right here gets substituted for a minus 1. It gets substituted for a minus 1, and you're using the Pythagorean identity. Tan square x plus 1 is equal to secant square x. If you bring the secant square on this side and 1 on the other side, tan square x minus secant square x is equal to minus 1. It doesn't matter what that x is. X could be any value in there. 2x, 3x, 4x, whatever. But this represents a Pythagorean identity which substitutes for a minus 1. Without me saying it too frequently, but look what happens over here. This right here became a minus 1, so we can write here tan 2x minus 1. This from here to here, this entire parentheses part is substituted by this tan 2x minus 1, because this tan 2x remained unmodified, but this part right here modified due to the Pythagorean identity. It modified by means of this process over here to a minus 1, so we get a tan 2x a minus 1. And then we can substitute this entire part for tan 2x minus 1, and our answer will be 2 secant 2x. Let's bring in the parentheses, tan 2x minus 1 divided by our denominator 1 plus tan 2x square, and we should be good with this answer. This here is a good final answer. Good. A difficult question, but not too hard. The simplification process was perhaps more difficult than the actual derivative process. Interesting question. Our function for this last question is this: cotan of root theta divided by sine square of theta. When I'm looking at this, I'm seeing a rational function, so I know I have to use a quotient rule. And I'm also seeing down here, this right here is my f and this right here is my g. My g function happens to be a composite function, so I have to use a chain rule. I have to do all of this for this question. So we proceed with the template for the quotient rule by starting with the sine squared theta, the g function, multiplying by the derivative of the, and actually I have a composite function right here in the numerator too. It's a composite function multiplied by the derivative of the f function, which we have to determine using the chain rule, minus the original f function cotan of root theta times the derivative of the g function, which will again involve the chain rule, all divided by sine squared theta to the power of 2, which will become sine to the 4th theta. So let's bring in the chain rule over here. Our first substitution will be here for this part right over here. Next substitution will be for this part over here. If u is equal to theta, actually if u is equal to root theta, then f of u is equal to cotan u. Let's put that over here. Let's put it over here, then we can erase it. If u is equal to root theta, then f of u is equal to cotan of u. And look at this next part. If v is equal to sine theta, then f of v is equal to v square. These are our substitutions we'll do over here. And depending on how much space we have, we can carry this to completion, or we can stop somewhere before completion, so long as the derivative part is done. Let's look over here. Sine squared theta times derivative with respect to u, and over here our u is cotan u. And you know cotan u yields you that, times derivative with respect to that theta for that u function was root theta minus cotan of root theta times derivative with respect to v over here was a v square, and then the derivative of that v function with respect to its theta value, which is going to be a sine theta. So now we've laid it out. Let's remove this and create our space, and then everything over here is over sine to the power of 4 theta, because this square and that square is sine to the power of 4. I believe in this next step we'll open everything up. We'll do sine squared theta. The derivative of cotan u is going to be minus cosecant square u, and derivative of root theta, anything which looks like that, you know now to be 1 over 2 root theta minus cotangent of root theta. V squared derivative would be 2v, sine theta derivative would be cosine theta. Now this is all over sine to the 4 theta. Alright, all of this is divided by this. Now in this next step, we'll do simplifying, but we won't take it to completion because that part is the algebra part, and we'll do substitution over here. Let's see over here. Sine squared theta times this minus 1 times this 1 over 2, you get a minus sine square theta cosecant square u. What's u over here? U was our what we substituted over here, root theta. That was our substitution here. Was u is equal to root theta over 2 root theta. Now look over here, you can't just take this minus sine squared theta and cancel it from cosecant squared theta. While they may be reciprocal, they're not the same because one is attached to a theta, one is attached to a root theta, so they're not cancelable. You cannot just cancel them out. Now let's look over here. You have a 2 and you have a cosine and you have a v over here. So let's just bring the 2 out at least, and let's bring the cosine theta with it. And we have this original cotangent of root theta, and you have a v. What did v represent over here? V represented sine theta, because that was our substitution. Now this is all over sine to the 4 theta. And you can see here the derivative part has been done. The derivative part has been done. You just have the simple algebra part now, or perhaps in the not so simple part over here of just taking this to completion. In terms of simplifying everything, you would basically have a common denominator over here of a 2 root theta. You would simplify all of this part out on the top to the extent possible, and then in the end you bring the 2 root theta down with the sine to the 4 theta, and you could rationalize that root theta if you wanted in the numerator and the denominator and take this to a final answer. But we're not doing that final answer because we don't have space over here. I just showed you the derivative part involved over here, and it seems like our question should be good. So as we wrap this video, just keep in mind up to now we've looked at the derivative of polynomials, which was not hard because that followed a specific scheme, and the scheme was easy. It was ax to the power of b. When you did the derivative, you did ba x to the power of b minus 1. Then we followed this by the chain rule, and we did the product rule, and then we've done the quotient rule also. And these were the videos we presented before this one. Now we've done the derivatives of the trigonometric functions, and you know these have not been hard, but they have involved the chain rule, the product rule, and the quotient rule to a significant extent. Now what will follow from here will be the other functions which we'll talk about. But remember, these derivative function questions can get quite complicated, but as they become more and more complicated, they perhaps lose their practicality or their practicable applicability. You want to be able to do questions to a reasonably comfortable extent. And of course in the textbooks, towards the end of each chapter, you know the questions get harder and harder. Having a solutions manual is very important. You can have questions which can involve very large chain rules. A question which would be something like this: sine, of cosine, of whatever, and then tan, and then root x. You can have all of these type of chains come into play, but then you're just basically running through automatic procedures over here. But you can test yourself or tease yourself with these type of questions. You'll have multiple kinks over here. And you could even have thrown in a denominator. You could have done all of this over like a different function like a secant x, and then made it a quotient rule on top of all of these chain rules. And you want to annoy yourself or you want to challenge yourself, you can do all of that. I'm just trying to keep the questions a little more applicable because I'm trying to teach you the techniques. But the main core of this video over here is this part over here. If you're given the sine and the cosine derivatives, you can literally derive the rest of these from just those two using the product, the chain rule, or the quotient rule, and I've shown you how to do that. The actual derivation of the sine x to the cosine x to the cosine x to the minus sine x, you can look that in the textbook. I'm not bringing that up because I'm trying to keep my videos more practical. But I hope you enjoyed this video. Please stay tuned for all the other functions that we'll be talking about in terms of their derivatives. It'll only get more interesting. It'll get a little harder, but it'll only get more interesting from here. But thank you for watching. Have a nice day. Bye.